In this video, we will explain how to generate design concepts. Do not start the concept design work until you complete the PDS though. Otherwise, you won't understand your task. To help you think of ideas for your product, study the design of competitive products. List their positive and negative attributes. If you see something negative in a design, don't copy it. As you develop your concept design, question the verbiage of your PDS. It's likely that you will want to change it. If so, go ahead. Just follow the procedures we outlined on how to do this. To get started with your concept design, have each team member think up a few of his or her own ideas first before you get together as a group. They can either make hand sketches, typically the fastest way, or noodle up a picture in CAD. Make sure to label the components in the sketch or nobody will understand your pictures. A time-honored method for creating concepts is to think of other designs that have analogs to what you're trying to develop. What mechanisms do you need for your product? And what other products can you find this mechanism? What changes to the mechanism will you need to use it in your design? For example, suppose you need a vacuum suctioning device in your product. Study a vacuum cleaner. How does a vacuum cleaner create vacuum? Another time-honored method is to participate in a brainstorming session. You get the group together, read the functional requirements from the PDS, and ask out loud, how would you design this mechanism? You write down the ideas on a whiteboard or in an electronic document, but don't judge them until they're all documented. You make up a list of pros and cons for each idea and move the best 3 or 4 ideas forward for further development. Another method you can use is to combine independent elements of 2 designs to create a new one. A good example of a combination is today's desktop printer, copier, scanner, and fax machines. 2 decades ago, 3 separate machines did these functions, but today you can get all functions for about $150 in one product at Best Buy. Subassemblies such as the optical scanner pull triple duty for the scan, copy, and fax functions. Beware, however, that you don't create a combination that is awkward and useless. Recently, I saw a 60-watt light bulb with Bluetooth connection selling for $12.88 in Home Depot. Without the Bluetooth connection, the bulb sells for $2.50. Are we really that lazy that we can't get up off the couch to turn a light switch on and off? At least when TV remotes came on the market, the companies that made the TVs didn't try to charge you extra for the remote. They just put one in the box with the TV. And do you want to spend $12.88 every time your light bulb in your house fails? It was bad enough when incandescent bulbs selling for $1 were taken off the market so that we could spend $2.50 on LED bulbs. But this is just getting ridiculous. The method of controlled convergence was created by Stuart Pugh in 1981 in his book entitled Total Design. Pugh was an engineering professor at the University of Strathclyde in Glasgow, Scotland. He was looking for a far more effective way of creating robust design concepts beyond the popular methods of brainstorming or weighted ratings. In Pugh's method, you alternatively converge on a final design by eliminating undesirable concepts and features, and diverge away from the final design when you hit a brick wall. This thinking takes broad concepts and narrows them down into workable designs. You take each alternative design and compare them to a prior art design, either a commercial product or a patent. You use a concept evaluation matrix to do this. The Excel form for this matrix residing in Blackboard under the item Template Documents. With this method, you eliminate concepts, create new ones as combinations, or temporarily diverge to some way-out ideas to get around brick walls in your thinking. Over time, you narrow down your thoughts to one concept. You should plan on at least 3 iterations through the evaluation matrix, each of which you document in your project reports this fall. Here's a diagram depicting how convergence and divergence work. Try using it in your project reports to describe your own experience with converging and diverging your designs. You can put little pictures of your own concept sketches inside the lines to show how the design progressed. Here's a screenshot of the concept evaluation matrix. The datum is the best prior art product or patent you found in your market research, the one that comes closest to solving the problem that you're working on. Sometimes you need to create independent matrices for more than one datum, typically the best patent and the best product. First, make quick sketches of the alternative concepts to the same level of detail. Create JPEG files of the sketches so that you can put them into the matrix. Place the JPEG files of the datum and each of your design concepts along the top row. Second, choose the most relevant criteria from the PDS to evaluate concepts. You put the criteria numbers or verbal descriptions of the criteria, if they're short enough, in the leftmost column. Comparisons are given scores of better, meaning plus, worse, minus, or satisfactory versus the datum. This is admittedly subjective, but usually reasonably easy to assess. Then, sum the total number of ratings. The strongest concepts will have the most pluses, some S's, and a couple of minus ratings. Weak concepts will have the most minuses, some S's, and a couple of pluses. Look at the minus ratings and determine how to improve them. This may force you to create new design sketches to illustrate how to address the weaknesses. If stronger concepts do not emerge, change the criteria in your PDS. There is a good chance that your criteria were too vague to allow you to evaluate the designs. If all concepts have equal ratings, you likely have concepts that are subsets of each other or too similar to be worth evaluating independently. In that case, redo your concepts to make them more mutually exclusive. And last, keep iterating with evaluations and updated design concepts until one very strong concept remains. This should take you 3 or more runs through the matrix. This slide summarizes how to use the matrix in case my verbal explanation was confusing or inaudible. Here's a sample of how to fill out the matrix, this time for fitting not only a square peg, but all types of shapes into a round hole. We use the square peg as the datum because it's the butt end of that tart comment, "That design is as awkward as trying to fit a square peg into a round hole." Not surprisingly, fitting a round peg into a round hole is rated most favorably compared to the datum, as well as the rectangular, triangular, hexagonal, and cross-shaped pegs. As part of your market research in your first project report, we want you to do a patent search relative to your design concepts. With over 9 million patents issued, it is likely that somebody has thought of an idea similar to yours. First, create about 10 keywords that describe your idea. Try to keep them fairly generic so that you don't do too narrow a patent search. Go to the website uspto.gov, move your mouse to Patents, and then click on Search for Patents. The next page will have a link that says How to Conduct a Preliminary U.S. Patent Search, a step-by-step strategy. This is a highly informative and fairly concise video tutorial on how to do a patent search. It's only 38 minutes long. Rather than listen to me describe how to do a patent search, listen to the experts at the Patent Office. I couldn't do as good a job as them anyway. Some of this info relates to the legal process, but it's still useful if you hope to get a patent of your own in the future. Slides 20 to 45 in the tutorial directly discuss the web search methods for finding patents similar to your concept. You can also click on the link for the 7-step strategy, which gives you handouts and screenshots for doing the patent search. Once you find the relative patent numbers, don't try to download the PDF files from the USPTO website. Use the Google Patents website instead, shown here with this web link. Type in the 7-digit patent number in the search box, hit enter, and the patent will come up. Once the screen comes up, click on Download PDF in the upper right-hand corner of the screen. Read the claims section at the end of the .pdf file to understand what aspects of the patent have been granted legal protection. Your patent search will give you a pile of patents that are relative to your project. You will need to skim through them and select the most relevant ones for further study. You must employ analytical calculations for concept evaluation before and after hand sketches or 3D models are created. These calculations must be based on the mechanical engineering classes you took in your sophomore and junior years. They could involve heat transfer, fluid mechanics, statics, dynamics, control theory, or my favorite, machine design. The results of these calculations will help you evaluate your design concepts relative to the datum. Here's a couple of examples of analytical calculations you might do. Heat transfer analysis for a power supply in an electronic module to determine if you need forced or free convection to keep it cool. Mechanical power calculation on a drive system to indicate the size of the motor you need, or a torque calculation on a drive system to indicate if belt and pulley, sprocket and chain, or gear system should be used. As you refine your design further and have significant CAD data, you may switch your static calculations from beam theory to finite elements. Ditto for heat transfer or fluid flow calculations. You all took CAD class, so I can assume you know all the basics of how to use a CAD system. In this slide, I give you a few tips on how to create a robust 3D model that won't require an endless number of changes to yield your part drawings. Make sure to use planar surface contact when mating rectangular elements and align your mounting holes with fasteners per a common axis. Also align your rotary elements such as wheels and bearings to a common axis. Most importantly, do not mate parts in space based on getting them, quote, eyeball close to each other. And more generally, follow these guidelines when creating your models. Wait to build a complex 3D assembly until you pick your final design concept. Otherwise, you may waste a lot of modeling time. Create abundant datum planes and axes to represent critical alignment references. And make sure the first few parts into the assembly are stable feature-wise. You'll likely reference these parts for your alignment references, and if you delete the first few parts, your future parts may lose their alignment references. Good luck with creating your design concepts. In the next video, we'll teach you about referencing engineering standards in your design and creating a project schedule to track your work.